I'm Professor Rad, and this is Precalc video 323, Solving Basic Trig Equations. In this video, we're going to look at 3 examples of solving some foundational level trigonometric equations. Then in the next few videos, actually, we're going to be looking at some more equations, but they will require more advanced techniques to solve. So we're going to lay the foundational techniques in this video, and then we'll be building on them in the next several. So for our first equation here, we want to solve 1 minus cosine theta equals 1/2. And we're solving this equation on 0 to 2 pi. So very often, because trig functions are periodic, you may be given an interval on which to look for your solutions. So we're going to be combining a few techniques that we've looked at in previous videos to solve this problem. First, we're going to approach this very similarly to how we solved for the inverse of a trig function. So what we're going to do is we're going to solve for cosine of theta to begin with. Just like when you were looking for an inverse of a trig function, you looked for solving for the trig function first, and then you rewrote it in terms of inverse trig or standard trig, depending on what you had. Then we're going to be using the technique of looking at our unit circle with that spiral of finding all theta in this particular region. That's going to equal a specific value. So let's go ahead and walk through this one. So I'm going to rewrite my equation. 1 minus cosine theta is 1/2. So to solve for cosine, let's subtract 1 from both sides first. So that will give me negative cosine theta is a negative 1/2. And then I can multiply both sides by -1, and that's going to give me cosine of theta is equal to a positive 1/2. So that's my first move here, is solving for the cosine of theta. Now, if I'm looking for an approximate value here, I could take cos inverse of both sides and use my calculator to come up with an approximate value. But for these examples, we're going to be looking for specific trig results, so specific values of theta. So what I'm going to do is I'm going to draw my unit circle. And I'm going to mark out the places where cosine can be 1/2. So when cosine is 1/2, that's going to be up here at pi thirds. And because cosine is the positive 1/2 and cosine is the x value, so here's about when x is 1/2, right? The other place is going to be down here at like a negative pi thirds. So because we're using pi thirds, I'm going to indicate with some dotted lines where my pi thirds are going to end up being. So like this is 1 pi third, 2 pi thirds, 3 pi thirds, 4 pi thirds, 5 pi thirds, and 6 pi thirds, and so on. Okay, so now that I've got my unit circle drawn out, I'm going to look on this interval from 0 to 2 pi. So this is where I'm going to draw that spiral. So we're going to start out at 0, and we're going to spiral around until we get to 2 pi, and we'll stop. Remember, if we had a negative value in this interval, we would then also go to the left, create kind of a second spiral going left. But in this case, we're just going from 0 to 2 pi. So my spiral intersects these lines in 2 places, once here and once down here. So that means theta is going to equal 1 pi third. This is 1, 2, 3, 4, 5 pi thirds. There we go. That's going to be our answer. Okay, let's take a look at this second example. So in the second example, it says find the general solution to cotangent of x over 2 equals -1. So there are 2 things that are different about this example from this first one. And I'm not talking that this one was cosine and this was cotangent. I mean, that's a difference, but that's not one of the big important ones. So the big important difference is that this one we had a specific interval, and this one we don't have that interval. So the second important information here is that we're looking for a general solution. So when you're looking for a general solution, what that means is you're going to need to write your solution as a set and you're going to need to list out all possibilities that theta can be. So in order for us to do this, we're going to be looking for some base solutions that we can look at, and then adding multiples of the period to get to the rest of the solutions. So for example, on this unit circle, on the last example, we would have had two base solutions to start out with. So I could have said pi thirds plus the period would get me back to here however many times I needed. And then same thing here at 5 pi thirds, I could have added multiples of the period as well. So let's see what that looks like, but this time we'll be using a cotangent instead. So the good news is this problem is already solved for cotangent. So we have cotangent of something is -1. So we really don't have to do too much in the way of rearranging or solving this equation. Most of our work is going to be in getting our base foundational values, and then figuring out how do I write this in a general format. So let's look at a unit circle. And cotangent is going to be a negative value in quadrants 2 and 4. And it's going to be a value that encompasses a 1 at pi fourths, right? Because that's when sine and cosine, or x and y, are the same. So we're going to have this angle here and this one down here. Also, I'm going to bear in mind that I'm going to need to find the period of cotangent of x over 2. Because once I find the period of that, that's going to help me to figure out what values of x, or like how many times around the circle I would need to go, basically. So if I look at what values these are going to be, since these are pi fourths, I can see that I'm going to have 1, 2, 3 pi over 4. So because this isn't just x, it's x over 2, I'm going to say that x over 2 could be 3 pi over 4, right? Because cotangent of this thing, so cotangent of 3 pi fourths would be -1. So that's why I need x over 2 to be 3 pi fourths. And if I solve that for x, I can multiply by 2, and that will give me 3 pi over 2. Now I can also look at this angle down here. Okay, this is a second kind of base place where I could get -1 for cotangent. In this instance, I could count around and get, what would that be, 7 pi over 4? Or I can go backwards and call it negative pi over 4. So that's what I'm going to do. I'm going to say that x over 2 could be negative pi over 4. So usually my personal preference is to find the fastest way to get to the angle. But if you used a positive 7 pi over 4, you will get the same solution set in the end. That's our goal. So I'm going to multiply both sides by 2, and that will give me x is negative pi halves. All right, so we found our base foundational points here. So our foundations are going to be at 3 pi halves and at negative pi halves. Then we're going to need to add multiples of the period. So I want to find the period of cotangent of x over 2. Now remember, when we were graphing trigonometric functions, if we have sine, cosine, secant, or cosecant, the period is 2 pi over omega. But for tangent or cotangent, the period is going to be pi over omega. Remember, this is because tangent and cotangent have a typical period of pi. So we need to divide by the coefficient of x to figure out what that period should be. So in this case, omega is going to be 1/2. So we have pi over 1/2, which is 2 pi. So we're going to end up with 3 pi over 2 plus 2k pi, where k is an integer. So that we're saying any full period. So if I did 1 full period or 2 periods or 3 periods, that's how often I'm going to be repeating. So 2k pi is going to indicate that we have an integer multiple of the period. So I'm going to start out by saying that we have the set of all x, so that x is 3 pi halves plus 2k pi, where k is an integer. I'm going to use the z for integer. That's a weird looking z. And then we have this other base value of negative pi halves, or x is negative pi halves plus 2k pi, where k is an integer. So if we wanted to write a solution that's going to work, this is a solution set that works. It's going to tell us all of the points that we want. This is what a mathematician would refer to as an inelegant solution, which means it's a little bit clunky. It's not the prettiest looking solution. And in fact, it contains some redundancies. So we can clean this up a little bit. For my purposes, for my classes, I'm okay with this because I need to know that you know how to solve for the particular values of x, and that we need to be adding multiples of the period. But if you want to make this a little bit prettier looking, let's look at how we could do that. So I'm just going to erase this previous example. So if I wanted to think about the kinds of values that I'm getting, so from here, if I have 3 pi over 2 plus 2k pi, well, if I add, if k is 1, then I could add 2 pi. If k is 2, then I would add 4 pi. If k is 3, then I would add 6 pi, and so on. So I could think about any patterns I'm noticing when I list out these values. So for example, on this one, this is going to be 7 pi over 2. This will be 11 pi over 2. And this one will be 15 pi over 2. So it looks like I could be adding 4 to each numerator as I'm going through. So another way that I could represent this is I could say we have 3 plus 4k pi over 2, where k is an integer. So I could do 3 plus like 0, 0 is an integer. So 3 plus 0 would give me that 3 pi over 2, which is our foundational value. If k is 1, we would have 3 plus 4, which is 7. That's our 7 pi over 2. If k is 2, that would give me 8. So 8 plus 3 is 11 pi, which will give me my 11 pi over 2, and so on. Now, I've only been looking at positive values of k. Let's also check negative values of k to make sure this would work. So I'm going to go back to this 3 pi over 2. And now instead of adding 2k pi, I'm going to subtract it. So if I have 3 pi over 2, I can subtract 2 pi. Or I could have 3 pi over 2, and I could subtract 4 pi, etc., and so on. So if I were to do this, that would give me a negative pi over 2. This one would give me negative 5 pi over 2, and so on. So let's see if these fit this mold. So if k is a negative 1, this would be 3 minus 4, which would give me my negative 1 pi over 2. If k is a negative 2, this would give me 3 minus 8, which would be a negative 5 pi over 2. So this is giving us all of our positive solutions and all of our negative solutions that we could get. Also, it's pointing out another redundancy that we had, which is that we had this additional sort of starting point of negative pi halves, and we can get there by using the other starting point So what that means is that these two starting points are actually not both needed. As long as I have one, I'm good to go. So to summarize all of this, this is the key expression that we're going to need. So another way to write the solution set would be the set of all theta, or x. We had x, right? Yeah. So the set of all x, so that x is 3 plus 4k pi over 2, where k is an integer. So this would be the much more concise way of writing this solution set. However, as I mentioned in my classes, I'm going to be totally fine with the clunkier one because it still expresses our solution. Redundancy is just redundancy. But if you're looking for something more elegant, more concise in your solution response, then this is what we're going to be looking for. All right, and then I have one more example for us to look at in this video. All right, so for our third and final example in this video, we're going to solve the equation 6 inverse cosecant of x is equal to pi. Now, one of the things that makes this equation different is that we have an inverse trig function in our equation. So because inverse trig functions come from a space where we've restricted the domain of the sine or the cosine or whatever trig function we're looking at. So because we have that restricted domain in place, that may impact how we solve this problem. So let's start out just by solving for inverse cosecant of x. And we can do that by dividing both sides by 6. So this will give me inverse cosecant of x is equal to pi over 6. Now, pi over 6 is an angle that's in the first quadrant. So I'm not going to have any trouble here when I go to continue solving. If I had something like inverse cosecant was equal to 7 pi over 6, then I would be in trouble. Here's why. So inverse cosecant has to spit out an angle that's in the east. So if I have 7 pi over 6, that would land me over here, and that's no good. So this equation would have no solutions. But since we're pi over 6, since we're over here, we're going to be good to go. So just do a quick domain check when you have an inverse trig function to make sure you're landing in the correct spot, either the range or the east or the north. Then remember that inverse cosecant is referring to an angle. So what this means is that cosecant of pi over 6 is equal to this value for x. So we can rewrite this equation using a regular trig function, cosecant of pi over 6, and that's going to equal the value that we're trying to undo with the inverse cosecant. This is also similar to when we were looking for the inverse of a trigonometric function, and you can think of this one as taking cosecant of both sides. So cosecant of inverse cosecant is going to cancel out to give us x, and then we have cosecant of pi over 6. So now we just have to find what is cosecant of pi over 6. So this is one we're supposed to know about. So if I think about the coordinates of pi over 6, that's going to be root 3 over 2, 1/2. Cosecant is going to be the reciprocal of the y value. So we're taking the reciprocal of 1/2, which is 2. There we go. That's how we solve that equation. So these 3 examples are different types of examples to lay the foundation for solving trig equations. In our next video, we're going to be building on these examples by not only applying these techniques of getting general solutions or looking in a specific domain, but also applying other trig identities, specifically double angle formulas and Pythagorean identities to help us solve. So I'm looking forward to seeing you in that video. I hope this video helped you to solve trig equations a little bit, and yeah, I hope you have a wonderful day. Bye for now.